Hi everyone, it's great to connect with you. I'm Aero and I'm currently in Toulouse, France. Here in Toulouse, you'll find the Airbus headquarters. I've been invited by Airbus to attend a conference where I'll be discussing the latest advancements in aviation technology and sharing some exclusive insights that are not commonly available. This is where the Airbus A350 is assembled. It's called the final assembly line. Before the Airbus Summit, they arranged a special tour exclusively for influencers, allowing me to experience it firsthand. This tour takes place at the core facility in Toulouse, France, where the A350 aircraft undergoes its final assembly. This particular building has been named in honor of Roger Bettet, who is a notable figure in the history of Airbus. He was an engineer and the lead engineer for the development of the first commercial aircraft, the A300. He developed the innovative idea of designing a common cockpit, which involved standardizing the cockpit instruments and controls to be similar across various aircraft models. He is regarded as one of the key founding figures of Airbus. We're here at the A350 line. Wow. The A350 is Airbus's flagship aircraft. It's built for medium to long-haul flights. It uses carbon fiber to boost fuel efficiency with its efficient engines. I flew on the A350 from Seoul to Paris. Airbus has its component production lines spread across various locations. In Europe, the production is organized so that the wings are manufactured in one location, while the vertical tailplanes are made in Hamburg. All these parts are then brought together here at the final assembly line in Toulouse. The A350's final assembly line is in Toulouse. The A320 family is assembled in Hamburg and Toulouse. The A350, A320, and A330 are assembled in Toulouse. The A220 is assembled in Canada and the USA. Parts from these places come together to complete the aircraft. From the front, you can see the assembly line layout. This diagram shows it clearly. The A350 facility, established in 2012, covers an area comparable to 15 to 16 football fields. It's quite impressive, wouldn't you agree? And as I'll mention later, Airbus is very committed to sustainable energy. A significant portion of the power needed for this assembly line comes from green energy sources. They've installed solar panels on the building's roof and used recycled materials for about 40% of the construction. The A350 is well known, and many of you might already be aware of its exceptional long-haul capabilities. Among currently operating aircraft, it's the only one that can efficiently fly ultra-long routes of over 8,000 nautical miles. 1 nautical mile is about 1.85 kilometers, so that's roughly 15,000 kilometers. The Earth's circumference is about 40,000 kilometers, so it can cover roughly a third of that. That's incredibly far. About 70% of the A350's weight is carbon fiber reinforced plastic. Using advanced materials like CFRP or titanium alloy, which are both light and strong, is key. Especially CFRP, which is much lighter than steel, but even stronger. When the aircraft is lighter, it consumes less fuel, which in turn allows it to cover much greater distances. Of course, using advanced materials can make the aircraft more expensive, just like how the iPhone got pricier when they used titanium. The materials themselves are costly, and they also need to be processed. While it's true that these materials are expensive, airlines don't just base their decision on the aircraft's price alone. The A350, with its exceptional fuel efficiency, significantly reduces operating expenses over time, which makes it highly competitive and appealing in the aviation market. The A350 is renowned for its wing design, which is optimized for efficiency. Most major airport gates are built to accommodate wingspans less than 65 meters, referred to as Code E. The A350's wingspan is 64.75 meters. It fits within the limits. Therefore, while enhancing the wing's performance, they also meticulously crafted the design to meet airport operational limitations. And that red section you see at the front is known as the radome. It's the pointed, cone-shaped part located right at the nose of the aircraft. During flight, it contains a weather radar. This radar detects weather conditions. I learned the radome isn't made of metal. It's made of a special composite. This lets radar waves pass through easily. It also protects the radar from outside elements. It has a special coating to improve radar wave transmission. This starts at Station 59. As station numbers decrease, the aircraft nears completion. Stations 59 to 50 handle fuselage assembly. Important tasks happen here. To ensure perfect accuracy in aligning the aircraft's front, middle, and rear sections, the process employs laser technology, which is crucial for placing every component precisely in its designated location. What truly impressed me was the technicians' meticulous work of manually inserting about 12,000 metal fasteners, known as rivets, to secure the fuselage sections together. Although some automated equipment is used, the crucial joining work is done by hand. I was curious about the potential risks of doing this manually, so I inquired further. They assured me that the entire procedure is meticulously controlled. From drilling the rivet holes to inserting and securing them, every step adheres to strict standards. Interestingly, the technicians are trained to apply the rivets with precise force and accuracy using specialized tools. The rivets, in fact, are not just simple fasteners. When they are inserted, they cause the body of the rivet to undergo a slight expansion. It's a bit like when you fix a flat tire, you insert something to hold it in place. Since they expand to fill the hole when inserted, I wondered if doing it manually might be risky. But actually, there are parts of the process where manual work allows for more precision. They also explained that sealant is meticulously applied between the rivet joints and the metal sheets to ensure no air or water can seep through, enhancing the structural integrity. Earlier at Station 50, we saw the assembly without the wings attached. Now, here at Station 40, we can see the wings being integrated into the assembly. In factories we're used to back home, there's often more mechanical movement or automation. It's similar to what you'd find in semiconductor plants. However, here, some tasks still require manual work. This makes the factory operations seem a bit slow. At Station 40, for example, the wings are being attached. The main and tail wings are here. A pair of large wings from the UK is attached to the fuselage center. Originally it looked like a sausage, but by attaching the wings, the aircraft finally takes on its iconic bird shape here at Station 40. Parts are assembled here. Complex systems are also installed. This takes 21 days at this station. They carry out the assembly work for a very long time. Once the assembly at Station 40 is finished, you'll see the aircraft with its fuselage, wings, and tail all assembled. At this point, the aircraft can rest on its own wheels and be moved around using a tug vehicle. However, since the engines are not yet installed, it cannot move independently. Our next stop is Station 30. Now we start installing the cabin. This is when the aircraft receives its first power. First, we set up the passenger area. This is called the cabin. This process includes starting the interior construction, such as installing wall panels, ceiling panels, and the overhead bins. Next, we attach what is known as a winglet, which is the small, slightly upturned section at the tip of the wing. These winglets are designed to minimize drag at the wingtips during flight, which enhances fuel efficiency. And at last, we provide power to the aircraft for the first time, marking a significant milestone at this station. When power is supplied for the first time, the cockpit and cabin lights come on, and various electronic devices start up, much like when you first boot up a computer. They test the lighting and ventilation systems. They also check basic flight instruments while the power is on. Following Station 18, the aircraft exits the assembly hall to have its engines installed and to undergo testing at a dedicated outdoor facility, much like a hangar. Following this, the Rolls-Royce engines are attached, and the final touches are added to the cabin, including the seating arrangements for first, business, and economy classes, along with the installation of lavatories. They conduct thorough ground tests and paint the aircraft according to the airline's design, followed by test flights. Once these steps are done, the aircraft is delivered to the customer. I was truly impressed by the assembly process here. Like other influencers, I found the Airbus Beluga transport aircraft especially fascinating. The A350 final assembly line has several stages. These stages are organized into work zones known as stations. Initially, as I mentioned before, parts produced at specialized Airbus facilities throughout Europe are brought here. These components are quite substantial, including sections like the fuselage, wings, and tail fins, and they arrive using a special transport aircraft. Now these parts are transported here by an aircraft known as the Beluga, named after the whale. It's named after the whale because of its shape. There's a version called the Beluga XL, which has an impressive transport capacity. It can carry 2 A350 wings at the same time. The front part of the Beluga opens up like a large drawer. It can be loaded very quickly. This Beluga isn't sold anywhere else. It's used exclusively for transporting Airbus parts, and was specifically designed for this purpose. The Beluga is essentially a modified version of the A300, where the lower fuselage remains intact, but a large cargo bay is added on top, giving it its unique whale-like look. The latest version, the Beluga XL, has been developed to carry even larger cargo. On our A350 final assembly line tour, we walked through the factory. We also saw how these aircraft are built. It was fascinating to see how the various parts of the aircraft are transported and assembled. What struck me about modern aviation technology is the remarkable combination of eco-friendly energy sources with the meticulous manual assembly of these enormous structures. Each component undergoes thorough checking and testing, rather than solely relying on automated systems, which I found truly impressive. Semiconductor factories work fast. They use a lot of automation. But because aircraft components aren't produced in such large quantities each year, the focus is more on stable and precise design and manufacturing. This tour really highlighted that aspect. Reporting from Toulouse, France, this was Aero.